And we talked about, let me get this first done so it works. Do you see the first slide? Yes, hopefully. We talked about monosaccharides and oligosaccharides the last time. So today we will focus on polysaccharides as the second part of carbohydrates and on their extraction and their analysis in the second part. So polysaccharides are very, very common. They are 90% of the plant material, and they occur as structural or as storage carbohydrates. So structural would keep a plant upright. For example, cellulose is a structural polysaccharide. And that is in all trees, in all plants, you imagine. And a storage carbohydrate would be starch. That is a way of a plant to store away sugars for bad times, so it can be used later. We can also get the polysaccharides out of marine sources, from red or brown seaweed, and there are very important ones like agar, you probably know, alginate, algin or alginate, you know, probably carrageenan. From animal sources, from the marine resources, from shellfish, the outside of shrimp, for example, is chitin, and you can make chitosan out of it. And you can get by microbial means some polysaccharides. This year's bacterial cellulose doesn't look very attractive, but it is a way of making polysaccharides. So we will first talk a little bit about their structure and then focus on starch, because that's a really important resource, and then discuss non-starch polysaccharides a little bit. And then in the end, I'll try to do some analysis. So let's start with the structure of polysaccharides. You can either have the repeat units, the monosaccharides, linked together by a glycosidic bond to form homoglycans, which means you have only one type of sugar unit as a repeat unit, or heteroglycans. They are made of different kinds. Hetero are much more common. Homoglycans, an example would be amylose or cellulose. It's basically made of glucose. Then we can have linear chains. Cellulose and amylose are linear or branched, like amylopectin, the second component in starch. The frequency and the length of the branching can vary, and it might be more regular or more irregular. And most are fairly complex. For example, pectin is highly complex, has a highly complex structure. Then we can have some of the OH, the functional groups of the polysaccharides, substituted as an acid group, for example, a carboxyl acid group, as a sulfato group, and we'll discuss that. So there are some conformational options. If these chains, these long polysaccharide chains, can align in a favorable way, they can form organized areas. And these organized areas can look like this, like double helices or triple helices, or just a helix. They can also be lined up parallel nicely and then form so-called crystalline or ordered regions. And those are these crystalline regions, they give support to the plant, they give strength to the polysaccharide, but they cannot be penetrated easily by water or any aqueous solutions. The areas in between the less ordered ones are responsible for swelling and things like that, and water absorption. So you have ordered and not non-ordered areas, and that depends on the structure of the polysaccharide. So functional properties and uses. I think the most important functional property is swelling and thickening. So thickening and gel formation is the major application for most of these polysaccharides. They can also stabilize emulsions and dispersions. They can form a film. They can be used as fillers. Fillers keep a product in a certain quality. For example, a crystalline product or a powder product, it keeps it powdery and doesn't make it cake together. They also add volume and lower the cost for the industry because they don't do anything but keeping the material in under certain condition. They have water holding capabilities and they keep the food moist. But most applications are really focused and based on the viscosity of their solutions and the swelling behavior in hot and cold water. You can have modifications. You can separate straight chain and branched molecules in some cases. For example, in starch, you can separate the straight amylose from the branched amylopectin, or you can derivatize and make the composition a little different. So you have options here, and it's done quite a lot. So there are many options. If you're looking for a specific functional property, you can choose different kinds of polysaccharides that fulfill that property. Thickening, they basically all do, but sometimes some polysaccharides fit a little bit better to a specific property and for a specific product than others. For example, here, if you want to thicken anything with fruit to make jams, jellies, whatever, pectin is a good choice because pectin is isolated from the peel of fruits. So that fits pretty nicely. If you want to make a jelly from fish or meat, a marine source polysaccharide might fit better, for example, agar or carrageenan. So that's for aspik, if you know the word in Indonesia too. Otherwise, you have a wild choice of different polysaccharides, and very often they are used in mixtures, various mixtures. So the impact of the polymer chain has a real impact on its properties too. So perfectly linear polysaccharides, that means one type of a neutral monosaccharide as a repeat unit, like in cellulose, you have glucose, in amylose, we have glucose. They are straight chains and they can form interactions between these chains, and these areas are then basically locked up more or less. Those are the crystalline areas that I mentioned before. They get ordered, they give strength, but they keep water out. So there's no way water can penetrate. If you have branched polysaccharides, it's much more difficult to stack them accordingly. So for example, here, just a fictive polysaccharide with this arm here. That arm can go in different directions and it can be longer, can be shorter. There can be another arm going up here. So these have a higher swelling power because they're more accessible to water, but they are less ordered and less strong. And an example is amylopectin or glycogen as well. And then we can have linear branched, so-called linear branched ones, which mean they have a long backbone and then short branches. And sometimes these branches are always the same kind. Sometimes there are different ones. Sometimes they are in a fairly regular distance, and most cases it's not. Again, pectin is one of those that has areas that are called hairy areas because of that. So it might look like this, a longer one, short, whatever. So water solubility is a really important aspect, and the different standardizing organizations define it in different ways. They define dietary fibers in different ways. And one of dietary fiber definition also comes with a solubility um, um, condition. So it's the question, soluble, insoluble in water, and it's a difficult question, really. The monomers must interact with water. That is no problem for any of the different polysaccharides, because really in most cases, the monosaccharides are water soluble. Some of them are even charged. So they are able to form hydrogen bonds. Now, some polysaccharides show an apparent solubility. That means they look like they are soluble, but if you give them some time, they will aggregate and then phase separate out. So they were not really soluble. And the opposite can be the case. They can have a very slow solubility. So they seem soluble, but it's a matter of time until they really go in solution. But they will dissolve over time. Temperature plays a role. Most dissolve easier in high temperature, but there are some cellulose derivatives where it is the opposite. Now, what is really a big issue is you cannot see polysaccharides separately in terms of food. In food, polysaccharides are together with other polymers on macromolecules, let's put it that way, like proteins, for example. And they might behave differently if they are together with other macromolecules. So now the all-encompassing question really is, what is a gel and how do we form it? What do we need for gel formation? By definition, a gel is a continuous three-dimensional network of connected molecules. How that network looks like is left open. It can be crystals, it can be droplets, it can be small particles. And the whole thing is in a continuous liquid phase. In our case, that would be water, I would say. So it has the properties of a solid and a liquid at the same time. The three-dimensional network, the network here offers resistance to stress, and it holds it in shape. So gels are considered viscoelastic semi-solids. That means between liquid and an elastic solid, viscous liquid and an elastic solid. It resists stress to a certain amount, but not forever. Imagine pudding. If you touch it just slightly, it will resist, it will remain in the form it was. But if you press hard, pudding is going to be flattened. So it's in between a viscous liquid and an elastic solid. Interactions are possible, hydrogen bonding, of course. Since we're dealing with water, liquid phase, covalent bonds, cross-linking can happen, and physical entanglements. Usually, people talk about junction zones that tie the whole thing together without really defining which of the interactions are really at work here. Junction zones develop over time. So 2 chains, 3 chains, more chains come together and they form some sort of an organized area here that holds the gel together, gives it the strength. It presses water out, and that process is called syneresis. Syneresis means that the gel is repulsing the liquid, comes out, the water comes out. The concentration of a gel is usually 2% of the polysaccharide, so the rest is water, but they are fairly strong, especially, for example, aspic. I don't know if you've seen that, if it is in a gel, if meat or fish and vegetables are put in a gel, it's fairly solid. Pudding, not so much, jams, not so much. Pet food can be pretty solid too. So the choice of the polysaccharide, which one you pick for your gel, depends on its rheological behavior. In rheology, is the signs of flow and deformation. So the viscosity is a function of the size and the shape and the conformation of the polymer. We need some flexibility so the polymer can be formed into what you needed, and we need some ordered and stiff areas, stiff coils. So depending on how that polymer looks like, it picks up a certain hydrodynamic average, like a little sphere or whatever, a shape. This depends on the general stiffness and how much the chain can unfold here. This will determine the space it takes. So linear chains have high viscosities and they stretch out more. So they take more space than the same chain or the polymer with the same molecular weight in a branched organization. So this fits together. It doesn't pick up as much space. Now, if you have a charged chain, it gets bigger even more because these charges try to be away from each other as much as they can. So the viscosity goes up, but the viscosity is then depending on the pH and the salt content, because counter ions will neutralize the charge, and salt is almost always in food. You have to consider that. And so the space will be less that a non-charged chain takes up. And so the viscosity is going down. So all of this impacts the thickening ability of polysaccharides. Now you select a polysaccharide or a mixture of polysaccharides depending on what you want in the end product. Do you want more solid-like consistency or do you want a softer gel? And so we have so many possibilities. For example, cellulose derivatives do well in cream cheese. They give this soft gel-like consistency and this creamy consistency, maybe without a whole lot of cream. Pectin, as we already said, works really well with fruit because it's obtained from fruit. Alginate works also well. Alginate doesn't have any taste or anything, can also be used very easily here. Carrageenan for meat and fish and veggie jellies. And then hot and cold temperature thickening, there are a few where the temperature isn't that decisive. And carrageenan, for example, offers a thickness of the gel in a wide temperature range. So you can have instant products as well. They form with cold milk, for example. So you pick a polysaccharide for whatever you can imagine. Now, the industry, if you ask the industry what they want, of course, they want low cost. Of course, they want reliable gel formation. So neutral unbranched monoglucans with one unit, like amylose, they tend to aggregate and crystallize much faster than amylopectin. And so they say, well, let's have just one component if we can. Remove amylose, which is in a lower content anyway, and just use amylopectin, call it waxy starch, and we have a reliable product in terms of thickening. They say, okay, fine, we can also maybe deal with derivatized glucans better. Some come with other functional groups than the OH group naturally, but we can also do it chemically. And then we know what we are dealing with, and we know what kind of gel formation we have. Charged polysaccharides, viscosity and gel formation, as we said, depends on the pH and the salts to control. But sometimes this might be easier for the industry to have a charge, know that this will exactly at pH 3 or, for example, 3 or 4, whatever gel, And with a certain amount of salts, we will get a specific viscosity. So the industry is always looking for something reliable they can count on. Now let's look at the functional groups that we can choose from. Carboxylic acids, very common. They come naturally in pectin alginate. They can be introduced in modified or derivatized cellulose, for example, carboxymethyl cellulose, or in derivatized starch, also possible. There are properties that they have a negative charge in neutral and alkaline solution. This proton is going to come off. And then you have options of gel setting at specific pHs, for example, with a 1 or 2 valent cation. We can use stronger acidic groups, sulfuric acid esters or phosphoric acid esters. Naturally in carrageenan, in xanthan, they can be introduced into starch, more common than cellulose, and you get water-soluble, highly viscous solutions. You can have combinations of the two. You can also have a combination with a positive charged. I told you we can isolate chitosan or make chitosan out of chitin from shellfish waste. That has an amino group here, and it can be charged positive. So we can have a gel with a negative and a positive component and form ionic networks. Very nice. And we can make the OH group, which is hydrophilic, and make it into a more hydrophobic, either ether or ester group. These here are ether groups. So a methyl ether or an ethyl ether. Then there are more less water soluble, but more soluble in organic solvents. And sometimes alcohol is an interesting fact here, option. And then we can, of course, lower the dP, chop it down, make it shorter. The shorter, the less viscous the solution. So let's look into specific polysaccharides and spend some time with starch. Starch is huge, huge, huge. We have native starch, a large component of the market. We have modified starch, which is either modified by derivatization or by other means, like shorter chains, like separation of amylose and amylopectin. We have a large area where starch is made into sweeteners, which means you have to break it down because only small saccharides have sweetening power. Here is another look at starch market. You see here the food market is 7%. It's funny that they don't say beverages, they say beer, 7%. But the major part is starch sugar. Now, this is not all sugar for sweetening. Some of it goes into manufacturing of bioalcohol for many products, as well as when you get gas at the gas station, and it says 10% bioalcohol that is made from starch. It is also the basis of many biopolymers that are hopefully in the future replacing the standard polymers that are not very environmentally friendly, while biopolymers are. So that's an overview and a projection to the next 4 or 5 years. Okay, how do we get starch out of tubers, potatoes, cassava, yams, whatever? So we start with this, for example. We do a washing, then a shredding and crushing, and the pulp here is not wasted. It is used as animal feed. So this goes away. Then we get starch milk. We concentrate it up and dry it, and then we end up with the starch powder. That's fairly straightforward and relatively easy to do. So that is also making this starch a very a favorite product of the industry. You can see it grows in many, many plants. It works with potatoes, but potatoes have a high value as nutrition, but also from monocultures of corn, for example, United States, endless cornfields, and it all is used to produce starch. Starch itself, we said it already, is amylose, straight chain, glycosidic linkage. Here you see that, or where the arrow is. It contains, it's in 20 to 30% in starch, and the other 70 to 80% are amylopectin, and that's the branched version. So here is the backbone, and then there are branches going off. You can remove the amylose practically completely, then you have 100% amylopectin, and that's waxy starch. We already mentioned that. Endless possibilities for extraction. Now, starch looks very different depending on the source. You have many sources, but you get different granules. These granules here are from potato starch. There are larger ones and some really small ones. Some are much larger from other sources. Some are more, the size distribution is more even. You get same size, more same size. You can get bigger ones. Some are more triangular, many variations. If you look in the internet for starch granules, you'll find many pictures. Now, a funny phenomena is that if you cut through one of these, you cut under the microscope, you cut this, and you see growth rings like a tree. And for many years, scientists didn't know what to say to that. They were puzzled. Now, today we know these are growth rings of amorphous and semi-crystalline or crystalline areas, which alternate here. Now, this here is amylopectin, how it looks like on the grand scheme. It's double helices coming off a branch, like a tree, really. And many of these together. Amylose itself is interspersed in here. It's a straight chain, just a regular chain goes through here. These areas here can organize in here and form hydrogen bonding, for example, and other possibilities, and then have some loose organized areas where water can penetrate. So that's how those growth rings come together. Now, the gelation of starch, that is really an interesting and in a way funny process. And the industry doesn't like it in that form at all because it's so little controllable. Depending on the starch, it will start forming a gel at 50, 60, 70 degrees. At room temperature, it's a dispersion, a slurry. People talk about slurries. It's a dispersion, little particle, undissolved, unswollen, nothing. It has a certain onset temperature here when the swelling begins, and then it reaches a maximum. This maximum is by far not at 100 degrees centigrade. It also varies with the type of starch. Once it passes that maximum, the viscosity goes down again because these granules start breaking apart. So it's very hard to control in this whole area, and the industry is not happy with it. Then eventually, gelatinization is complete. However, the gel changes again when it cools down. And here, amylose crystallizes or ages faster than amylopectin because amylose is a straight chain. This process here is retrogradation, called retrogradation. So starches are different. Wheat starch, potato starch. I should have picked a different one here because they are very close in terms of the onset. In this case, 56 here, 60 degrees centigrade. Maximum gelation in this case is the same, close to 70 degrees, but you see it's far from boiling. But the water binding is quite different here between the two. And the swelling ratio is very different. So if you want something that swells more, you would need potato starch. Now, on a molecular level, this here is amylopectin, and this here is the amylose going through. During swelling, water enters here and presses this construct apart somewhat. Amylose is forced to the outside, so it's now at the outside. If there are shorter chains, they might even go in solution at higher temperature, so they are dissolved, they're gone. The others are pressed to the outside, and the water molecules are in here, and the swelling occurs. Now, when you cool, amylose in solution is just single chains floating around. If you do a fast cooling, you kind of freeze that process, that structure and interactions form between these chains and hold the gel. This will rearrange over time. This isn't the end of the arrangement here. If you do a slow cooling, these chains have time to align better and form more crystalline structure. So this here is terminated earlier and it's more organized than this here. This will continue on. Now, what effects does this have on our food product? I have a flying bread here. So when does it get stale? It actually, frustratingly, goes stale as it cools. It looks nice when it's fresh, but it does start the staling process during cooling because the starch transforms from amorphous to crystalline retrograded state, and the amylose is done by the time the bread is cool. While amylopectin is still busy for a while reassociating and then crystallizing or finding its final structure. So if you want to control this, you might add some lipids, some fats that have surfactant properties to the baking process. You can see that different bakeries, commercial bakeries, baking factories use different recipes. And if you pay attention, some breads get stale very fast, and some other breads are fresh a lot longer, and that depends on their baking recipe. I don't know what is better, but you decide. So if we don't like what we see, the industry will say, I'm not going to deal with starch straight away. We want something that we can rely on. We want to tailor the functional properties. So we have some options if we look at starch. We have options with others too, but let's look at starch. First, we can mechanically damage starch granules. There is some damage done during the grinding process. If you remember the potato that we made into starch milk, and then continued on into starch powder. The mechanical action to grind that potato already causes some damage to the granules. If they are damaged, water can more easily being picked up and the chelation temperature comes down. But if you want to control it, you will have to look closely how to do this and maybe find a process to make this uniform. You can make starch ethers, the OH groups, the proton replaced by an R, and the R could be a methyl group, for example, that can help with some of the functional properties. You can cross-link starch. That is a stabilization process of the starch. It will increase the gelatinization temperature. It will also decrease the swelling power because you have cross-links, which means linking parts and pieces of the structure together that are not broken during the swelling process, but it can be helpful if you do it controlled. You can also oxidize the OH group and get a negatively charged group. This is used for low viscosity fillers in salad dressings. They don't need to be that gel-like really, but they need to have some consistency. And if you do that, retrogradation is going to be difficult. So hydrolysis, we can break down polysaccharides somewhat and control viscosity with that. There is wanted hydrolysis. You do it by purpose to form smaller sugars or to form sugars altogether, simple sugars. That's called digestion. We talked about this earlier on. That's a way of making glucose or sugars for sweetening with sweetening power, or sugar alcohols. And then there is unwanted that always happens during the processing or the storage. How do we do it? We can go with acid, chemical means, and use acids, or we use enzymes. If you do enzymes, we have to be really careful with the temperature and the pH. Enzymes are very picky about that. We use highly specific enzymes that break down the polysaccharide chains. And I'm sure you know, if the ending here is ase, it means it's an enzyme, and the front of the enzyme word name is usually the food this enzyme is living on. So amylase will break down amylose, and pectinase will break down pectin, and cellulase will break down cellulose, and so on. If you have shorter chains, you have a changed viscosity, so you get a different rheological behavior. To avoid it, you can either select more acid-stable polysaccharides. That makes sense if you have acidic foods like fruit-containing foods. You might pick a different polysaccharide altogether. Or you can use higher viscosity grade polysaccharides. That's also a possibility. So how do we do it? In starch, we have several possibilities. We can spray with an acid. That gives you so-called acid-modified, thin boiling, thin or fluidity starches, different names for the same thing. So we have weakened granules, few glycosidic bonds are broken with this, spraying with HCl. And we can use it for coatings mostly, nuts, for example, jelly beans. We can use a stronger acid treatment, and we get dextrins. Those are linear chains, lower viscosity. They have film forming capabilities. They are very often used as carriers for flavor and sometimes for cold water soluble gels. You can do an incomplete acid or an enzymatic hydrolysis. That means you stop the enzyme hydrolysis, for example, by changing the pH or the temperature. That will end it. That's the easiest way. And you get malto-oligosaccharides. Those are oligosaccharides with a DP of 5 to 20. So really short chain. You can get some more bulk in food, but these are not sweet yet. And then you can do a complete hydrolysis, as we said, and you get glucose, and glucose can be concentrated up into a syrup. You can get all kinds of syrups this way. They are so concentrated that microorganisms do not attack them, and they don't need preservatives anymore. So these are the options, some of the options for starches modified by acid hydrolysis. Now, the modified starch market is big. Unfortunately, there are no numbers, but the food and beverage takes the biggest sector. Animal feed is also pretty big, and the rest here are more industrial segments. Pharmaceuticals is really important, and then paper industry here does a lot with modified starch because there are adhesives as well. So what about non-starch polysaccharides? We have cellulose, we have pectins, we have food gums, and we'll discuss some of those briefly. Cellulose itself is not useful for human digestive system. We can't deal with it. We are no cows. So it's a dietary fiber. It doesn't have calories. It doesn't have any nutritional value. But we can probably modify it, and we get to that in the next slide. So it has straight chains, no branches, very high DP, larger than 10,000, 14,000, even more in native cellulose. You can tell that these can stack nicely. Just take the same thing and put it in several layers here. So we have 60 and up to 90% crystalline areas in, for example, in cotton, you have 90% crystalline areas, very strong structures and not really digestible. You can isolate these crystalline areas and make microcrystalline cellulose. What you just dissolve the less ordered areas and the crystalline areas are left over. And then you can add them to low-calorie salad dressings or as fillers or whatever you want. But they are not digestible either. Now, cellulose derivatives, cellulose ethers are important, esters too, but let's look at the ether here, methyl ether. The viscosity drops with rising temperature, so it gets thinner when you warm it up. These are shorter chain celluloses too. If you have, let's say, 14,000 dp in methyl cellulose, maybe you have 1,000 or 800 dp, so a huge drop. You can have, with this behavior, a cold setting gel. It depends on the dp, on the length of the chain, but also on the degree of substitution and on the type of the substituent here. Degree of substitution means how many of these OH groups have been made in OCH3 groups. You have basically 3 that you can use. So your DP is rarely 3 because your DS is rarely 3. It will be somewhere between maybe 1 or 0.5 and 2. Because if you substitute too many, then the product gets more and more hydrophobic. You still want it to be water soluble and responding to water. So in baking, you can use it for gluten-free products. You can use it in diet food because it feels like you have eaten a lot. It swells in your stomach. And so if you want to lose weight, some of the diet food contains methyl cellulose to make you feel full. It's also used, by the way, as glue for wallpaper. So think about what you're eating. And it can help with some other properties as well. The cellulose derivative market, you see food and beverage is about 1/4 here. The rest is all more technical uses. It's in pharmaceutical and cosmetics used a lot, but then also as plastic materials, textile materials, and so on. Now, pectin is more interesting for food, but it's highly complicated. It has about 65% galacturonic acid as a repeat unit. It has negative charges. Not all of these R groups are replaced with an acid group. Some of them are also methylated. It is obtained from the peel of fruits, which is kind of a nice source because usually the fruit itself is made into jams and jellies and applesauce and whatnot, and the peel is left over. So it's kind of a nice use of the waste product. But it really is a family of compounds. It's not just one, it's a family. So we have various different options. It's stable at very low pH. So pectins, half of them, if more than half of them are as ester groups, you talk about high methoxylpectin, HM pectin. That these gels are useful in jellies and fruit jams. And if you have less than 5%, 50%, you have LM pectin, so low methyl ester content. And you can use these for low sugar jams and also for other thickening. For example, yogurt is thickened with it. All of this, everything that is a little bit acidic, pectin is a good gelling agent. On the side, if you want to get medication into your digestive system, bypassing the stomach, you can wrap it basically in pectin, and pectin will survive the stomach pH. Just imagine that. Now let's look at some gums. There are gums from trees. We have gum acacia, gum arabic. Those are tear gums, exudate gums. You see this little blob here. If you scratch the bark of the tree, it excretes some sort of a resin that is a gum. These trees where this is grown are mostly produced in the dry areas of Africa, Nigeria, Senegal, Sudan, Chad, and so on, but also in Australia and India. In Africa, the problem is these areas are very dry for once, and the other thing is there are very often conflicts, wars, and things like that. And that makes it a little bit different for trade and economy. These are complex structures of about 70% polysaccharide and some proteins. In food gums, they are good to use as oil in water emulsifiers for incorporation of flavored compounds. And that's their major application, maybe besides a thickener. You can hide or get a citrus flavor into drinks using gum arabic. You can also use it for in baking, get citrus flavor into cookies, for example. They prevent the blooming of sugar on chocolate. That means if chocolate has been sitting for a while, it's a little bit old, it usually shows a white coating or a little white surface, and you can prevent it with gum acacia. Two other tear gums that are important, gum tragacan and caraya gum, they are obtained from shrubs, both one from Middle East, the other one from India. Water soluble and water insoluble with high swelling powder in this case. Thickeners in salad dressings and icing on baked goods, water binding in soft cheeses, gives body to food. So you will find these on the ingredients list sometimes. Caraya gum prevents syneresis of gel. The syneresis was the expulsion of water, remember? And the structural units, complex, galacturonic acid, rhamnose, and other sugars make it up. Guar gum is obtained from a seed. This here is from Amazon, which I think is funny. You can order it in Amazon. It binds in food, water in food, avoids ice crystal formation in ice cream. So you don't have the water sitting on top of the ice cream. It's used a lot in dairy products and pet food. Now, other storage polysaccharides from seed pods, we have locust bean gum. You find that on the ingredient list a lot too. It's obtained from mostly in the Mediterranean area. Is used a lot in salad dressings. So if you see that salad dressings is common, a binder in the meat industry, sometimes water is injected into meat, which is to a certain extent allowed, but I, as a consumer, find it disconcerting because you pay for water, not for the meat. So low-cost bean, gum, or flour might be added for that. The other one is tamarind flour, brown seed pods, comes from India. Good substitute for pectin if you don't have pectin. So it's used for the same things that you would use pectin. Also stabilizes ice cream and condiments. Now, inulin comes from these roots from many plants. They contain inulin in asparagus, in banana, onion, garlic. The DP is really low, only 60. That's a very short chain, but it's still considered a polysaccharide. It's made of 5 membered rings. It's a dietary fiber. It's very beneficial for our digestive system. So it's added a lot by purpose because of that. You need, however, a lot. You cannot make any gels below 25% inulin, so that's a lot. But if you make it, it mimics fat, and that might be worth the expense. So low-fat diet food, for example, breakfast bars, you name it, anything low-fat, you find additional fiber. It's usually inulin. It can cause diarrhea if you take too much of it, though. Now, a short excursion to chitin and a longer excursion to these 3 here. Carrageenan is really, really important, and alginate is too for food. So those come out of the ocean. You might know agar better from media, nutritive media and microbiology from your labs there. That is the most common use. Agar contains agarose and agaropectin, so it's also bicomponent fiber or material. It is in food indigestible. It is still added sometimes, especially you'll find it in yogurt. I've seen it on the ingredient list of yogurt or ice cream a lot. It retards bread staling, so you might find it there too, but I think it's more rare. Sometimes it's used in the meat substitute industry, but for the food, I'm not sure if agar is all that important. It's different for alginate. Alginate is obtained from brown algae, from the giant kelp that you find in many oceans, in hot and cold or warm and cold oceans. It is built of G blocks, hyaluronic acid, or M blocks, mannuronic acid, or GM blocks. So it's alternating here in a non-organized manner, of course. What's really important for gel formation are the G blocks. You can see that this is like a little basket here. There is space in here. Now, if you imagine the same chain on top here, you get a little round space, and we can put a calcium or other divalent cation in here. So here they go. These need to be long enough. I think it's 5 or 6, so we need more than I drew here. 5 or 6 of these G units together to fit enough calcium 2+ in here. You get a gel that has junction zones, remember junction zones, crystalline areas, or whatever you want to call it, aggregated areas that look like an egg box. So here is an egg box. That's why this structure is called an egg box structure. Alginate can form it, and pectin can form this kind of structure. Alginate in food is incredibly versatile. You can make fake foods with alginate. You can engineer foods. If there is cheap caviar in the grocery store, it's alginate, it's not caviar, it's not fish eggs, forget it. You can make onion rings, that's beyond me. Onions are so cheap, why would you replace an onion with alginate? You can make stuffed olives. The stuffing in the olives, the red stuffing, is very often alginate. It's not pepper or paprika. Maraschino cherries can be made of alginate. You can encapsulate food or flavor in the bubble tea, and I'm sure you've seen these bubble teas. There was a big fashionable thing to get bubble tea some years ago in Germany as well as in the United States. Everybody had to have bubble tea with these alginate bubbles on the bottom. Now, carrageenan is also very important. It is important because it can be used at very low concentrations. So it works very well. It has sulfate groups in the structure. There's a whole family of polysaccharides that belong to this carrageenan. The kappa carrageenan is the most important one. In solution, it looks like this. As soon as it crystallizes or it cools, it crystallizes and forms these double helices here. So the gel is stabilized by these double helices. The gel forms upon cooling, so it gets more solid the lower the temperature. And you can get a variety of gels. So this is really important. For some years, there was a health concern. I don't know what happened to it. We don't hear about it anymore, but you might want to check. So really briefly only, because for food, chitosan is not that decisive, not that important, but chitin itself is a waste of the seafood industry. You can relatively easily remove the protein, use a sodium hydroxide treatment and get chitosan out of it. This here is chitin. This is chitosan. You see the difference. These groups here have been split off and replaced by NH2. Now, this here gives you a polymer with a positive charge. This forms films very easily. And you can combine it with a negatively charged polysaccharide. This is more important maybe for packaging or things like that, film formation over food. It's non-toxic, it's fine, but it's less added to food. Now, bacteria, you might know this. I think I saw some research going on in your labs when I was in Indonesia. Visited your university. Cellulose can be produced by a bacterium like Aspergillus niger. It forms little fibrils and then forms this brownish gel kind of thing. It looks, I don't know, a little bit disgusting. You can purify it and then you get this clear gel. You can make these into clothing, by the way. You can look it up. There's a website of the London Museum, and you can make this into clothing that look like parchment. You just cannot get into the rain because it suffers. It will shrink in the rain. So nevertheless, you can make cellulose, bacterial cellulose, and that cellulose you can also eat. It is used in nata de coco, and I'm sure you've seen these. I think you have those in Indonesia too. Depending on what you use to make it, in what solution it's put, it picks up the flavor. So if you put lemon juice here or whatever, lychee or whatever, it picks up that flavor. And it is a nice gel for dessert. Xanthan gum is also made by bacteria. It's a little more complex, but it has a very nice property. It forms stable gels that's basically independent of the temperature, so no change in viscosity, so between 0 and 100 degrees. So you can use this for freezing, thawing, hot, cold, for different variety of different food products. And you can combine it, of course, with others. It has a backbone, and then every third or fourth, there is three oligosaccharide going off, so a branch going off. Okay, so we come to the last part, and let's discuss analysis of polysaccharides a little bit. I looked very hard to find some good analysis methods, but I could not find a whole lot. It's such a complex material, and starch is one thing, but the non-starch polysaccharides even worse. So we don't really have something good here, but I'll show you what I could find. First of all, total soluble and insoluble dietary fiber. The labeling on the food product requires a definition of the dietary fiber. However, there are different definitions depending on the standard institution and on the country and whatnot. Generally, this is the general agreed upon definition. Dietary fiber includes oligo and polysaccharides that are not broken down in the human digestive system. Plant cell material, this is cellulose, hemicellulose, lignin. I don't know if lignin really belongs to that resistant starch. That's called insoluble dietary fiber. And then pectin, digestible oligosaccharides, and a few others are soluble dietary fiber. And amylose and amylopectin are digestible. That's basically the only ones that are digestible. So all other polysaccharides belong to either insoluble or soluble dietary fiber, and the total dietary fiber is the sum of both. You just add it up. Okay, so what can we do? Again, depending on the standard organization, you'll find different procedures, but you can adjust them fairly easily. First, we dry and grind the sample. I would suggest vacuum drying to not do any damage, unnecessary damage. Then you remove the fat. We haven't talked about fats yet, but it's very easy to do with an organic solvent, petroleum, hexane, chloroform, whatever. Then you remove the organic solvent, and you measure also, you measure the loss of fat and moisture. You know how to measure moisture from Johannes' lecture. Then you treat it with a heat-stable amylase. You can get those, and they are available to break down the starch. And then you use a protease, break down the protein. Then you use an glycoamylase. That's an amylase that takes care of the short chains that are formed here. Then break those down. Then you use ethanol to separate, and the residue gives you insoluble dietary fiber, and the filtrate, what's on top, gives you the soluble dietary fiber. Okay, after enzymatic hydrolysis, you can determine the reducing sugar content. Specific hydrolyses are used to generate oligo and monosaccharides with the reducing sugars. These reducing sugars reduce copper 2 to copper 1 in alkaline solution. And then this copper 1 is reacted with a reagent made from ammonium molybdate and sodium arsenate and sulfuric acid. And that is reduced by the copper 1 that you got from here, and a highly blue complex is formed. And then you can measure the absorbance at 520. In order to get an idea how much you have, you need to create a standard curve of glucose versus its absorbance. So you have to do different concentrations of glucose, go through that whole procedure, and create a standard plot first, and then compare it to what you got with your compound. Well, it looks work intensive, but maybe it works. Now, you can do all carbohydrates, total carbohydrate content. For example, in soft drinks, you have mono, oligo, and polysaccharides and derivatives in the sample. Sulfuric acid, as you might remember from carbohydrates, works with all of them. It digests everything. Then you add phenol and heat. There is heat involved here by the digestion anyway. And then you add phenol and you get yellow condensation products with that phenol. And then you measure the absorbance in this range. Now you would have to run a standard curve as well. If you do not know what's in here, not at all, you use glucose with known concentrations and do the standard curve with that and get the absorbance for phenol complex with glucose at 490, compare it to that. It would be better, however, if you had some idea, let's say you know you have pectin or alginate or whatever, that you use a closely related sugar composition to make the standard curve. So if you have a dominant, let's say alginate or so, you'll go with the sugar combination and get standard curve with this. That would give you a better standard. But if you don't have any idea, use glucose. Again, it's kind of labor intensive. Now starch, the only reliable method to determine starch is a enzymatic hydrolysis to glucose. Okay, we know we can use alpha amylase to break down the linear chains. We can use isoamylase to get after the branched molecules. We produce some smaller molecules here. First, you would swell starch to make sure that the enzyme can get there. Again, enzymatic reactions are highly sensitive to pH and temperature. You want to do it always the same. You want to watch the pH range, use buffer solutions to get it, watch the temperature closely and do it always the same. You also want to check the activity of these because they might differ from lot to lot. Then after you have it broken down into smaller oligo and disaccharides, use amyloglucosidase, and that breaks down the smaller oligosaccharides and produces glucose. And now we're in business. Yeah. Hey? Did you have a question? No? Okay, so you get experimental error, unfortunately, because there is some resistant starch, for example, cross-linked starch or whatever. There's some ungelatinized portion of starch sometimes. So you want to be sure that you get mostly a gel here. It might be that there is some retrograded starch already. So there is some insecurity and experimental errors that you have to watch out for. Now, if you have non-starch polysaccharides, I have not found anything that's easy and that's clean and clear. It's easier if you always deal with the same type of food product that you're analyzing. But if you're one day analyzing soft drink, the next day some cookies, the following day baby food, it's really difficult. But if you're always analyzing the same, this might work. So the general procedure for this is you defat the sample with a solvent. You treat the fat-free sample with ethanol and extract soluble sugars and low molecular weight products. Then you remove the protein with protease. Same as enzyme for the protein, breaks it down. Then you add ethanol, treat the polysaccharide precipitate, which comes out of the solution, with enzymes to remove the starch. Then you centrifuge the sample. You get residue as insoluble fiber. You add ethanol to the soluble portion to remove the soluble fiber and the starch hydrolysis products. And then you go by dialysis. Remember dialysis? It's a tube with a semi-permeable membrane. You expose it and you get a red tintate. That's the word, that's what's inside the tubing, the tube. You freeze dry it and you dry it, you get the dry polysaccharide extract. And then you go with HPLC or GC analysis to identify the compounds. So this is a lengthy process and not really routine. I hope that it stays within the same type of polysaccharide. That would make it a lot easier. So if you always have only soft drinks, for example, then it's maybe easier. Now, a word on spectroscopic determinations. In food analysis books, I find very often, oh yeah, IR, FTIR is easy to do. It's easy from the experimental procedure, but the results, interpretation of the results is really not easy. Again, if you work with the same stuff all the time, it might. But if you try to separate between different compounds, it's really not easy. The top spectrum shows you a cleaned up with not much noise spectrum FTIR of gum arabic, the lower one carrageenan. This area is usually very similar because here's OH, every polysaccharide has OH. This here's CH, every one has CH. So it's kind of brave to get something out of here. And then you see how these points are labeled here. I find it really, really brave to put an error here. I don't really see much of a peak. And then the same here, you have so many peaks. To separate them and make sense, you really need a very clean sample and, if possible, a standard or something to it. But these are mixtures anyway, so I don't know if this is working well. I find it hard even for just cellulose or just starch to do this, but it is always mentioned, so I wanted to mention that. If you want to see the whole publication, it's down here where I got this from. So this gets us to the end of today's class on polysaccharides. And I will see you for the lipids after the break. So in the meantime, please check out what I posted in regard to the midterm assignment, and do let me know if it's not clear to you, or if you have a question, or if you want to ask me first which raw product you should be choosing or whatever. So please use my email and ask me. I will answer immediately unless it's in the middle of the night. So thank you very much. Do you have any question to the class? Yes. Yes, any question? No? Then thank you very much. Bye-bye. I'll see you in 2 or 3 weeks, whatever that is. Bye-bye.
Yep. Thank you so much.
Thank you.
Thank you.
Thank you.
You're so welcome.